Welcome back, Benedict.
Yeah.
So
Sorry.
I'll just kick this off. So my name is Vicente Barot. Thanks for everyone who has joined so far. Welcome to the LibreHub project. This is our project with Pauli Russell, Tobias Wenzel, and I are organizing with funding from Chan Zuckerberg Initiative, and is based in Catholic University in Chile. But today is our first seminar. We're kicking off a seminar series, and the topic of our project is to expand the access to open hardware bioimaging tools, especially for researchers in Latin America. And today we're launching our seminar series. We will kick off with the first talk from Benedict Diederich that is sharing with us today an interesting topic. And before we head to that, let me just mention that we will have, this will be a recurring seminar series. The next talk will be in 2 weeks. Esteban Vera from Catholic University in Valparaiso will be presenting. But we will share details later, and also we will probably have a calendar so you can keep up with the organization of the seminar series. And also another small announcement, we have some open positions to work with us in the LibreHub project. So if anyone knows anyone who might be interested, please let them know to contact us. So in our talk today, we'll hear from Benedict Diederich. He is a postdoctoral fellow at the Bio-Nanoimaging Group at the Leibniz Institute for Photonics Technologies. And he previously completed his PhD at the University of Jena. So welcome, Benedict. Thank you very much for joining us. And I'll now stop sharing so you can share your screen and tell us about the UC2 microscope. So we will have some time for questions, but if anyone has any quick interruption, I think that's probably okay. You can raise your hand and we can organize that.
Perfect.
So yeah. Benedict, I'll leave you to it.
Very nice. Thanks a lot. All right. So thanks a lot. Is it called Vicente, right? Sorry. Good. I'm assuming everybody can hear me, and maybe also seeing the slides. I'm trying to present everything that's already been published somewhere by means of open source. So I think we sometimes write publication, but in most of the cases we also publish stuff to GitHub. So everything which you will see here in some form has been published on GitHub. So if not, just write us and then we provide you additional information. I think that's also the core idea. What I'm trying to present you today is that open source is definitely helping research, not only your research, but also the research from others. And yeah, I'm giving you a quick tour, which may be very chaotic, but that's how life's going in our lab, especially. My name is Benedict Diederich, and as you already heard, I'm part of the Leibniz Institute for Photonic Technology, and in Jena, basically the place where microscopy was invented, more or less. The problem, or like microscopy in general, has a problem. And what you see here is something that does not have this problem in particular. It's a hammer, and I think everybody knows how to use it. And in microscopy or in optics in general, I think you have the problem that some setups are not really understandable. They behave more like a black box, and you never know what's really happening here. So this is a rendering I copied from Twitter. This is an actual setup from some people doing some quantum stuff, and I would have no idea how to replicate that. And so one thing we're trying to do is like changing that. And so I think another vision here is that many people are using microscopes and some are building them. What if you can put those two different groups together and fuse them in order to generate maybe even better ideas for future research? So I think microscopes are the perfect building bridge for whatever you want to do. And yeah, I will just start with that in my mind, or in your mind. And looking around, of course, microscopes is nothing new. So there will be tons of microscope on the market, some that give you high resolution, some may have high throughput, but all to some extent with the problem. So affordability, of course, is one thing. Accessibility is another thing. Adaptability by means of, for example, how can you adapt your sample? And then also availability. So sometimes a device may just become discontinued and then you cannot even buy any spare parts anymore. Luckily, there has been many efforts being done by people contributing to the open source environment by means of producing very nice microscopic instrumentation and also providing you with open source documentation, files, how to build them, print them. And so we are not alone, and we'll just step in the footsteps of giants, let's say, and continue the efforts being done already. I think one thing you can always keep in mind is like, does not necessarily have to be expensive. So for almost any part in the lower end here, which you usually find in high or like in these expensive labs, like, well, the one we are here right now, they are really expensive. And I'm always, being reminded that this is the wrong price. So a camera easily costs like 15,000 euro, which is roughly dollars. But there's, for example, the Raspberry Pi camera, which is quite reasonably cheap, or like an ESP32 for data acquisition and sensor readout, etc. So there's an alternative for all these scientific grade devices, but of course coming at the price that it may be not that easy to use. I think one thing I like the most is maybe the optical pickup. Let's have a look why it's so cool. If you observe these optical pickup devices, they are essentially small microscopes, like confocal microscopes. They have a little lens, they have a laser, and the laser has to be focused in order to read out the information that's sitting on this disk by means of these pits that represents a 1 or a digital 0. And so if you compare the different mechanisms like CD, DVD, Blu-ray, you have very high optical resolution. So it's going down to 130 nanometers. So you have to have a really well-aligned system that can read out these information optically. And there's, if you open one of those, so you can just get them for essentially €0 as a spare part or scrap heap. And so if you open them, you will find tons of optical stuff there. So there's a beam splitter, dichroics, there's lasers, there are small voice call mirrors that enable you to precisely focus a beam up to some 50 nanometer precision. And we made use out of these devices for our research. And well, one thing we are interested in particular is imaging fluorescent cells. So here you see a kind of blurry image from microtubule labeled HeLa cells. And so we published that already quite a while ago, and we wanted to demonstrate, or we asked ourselves the question, is it possible to do super resolution imaging by means of optical resolution with a cell phone? And yes, it's possible. So this was the result back then. And the core question was, how can we do that? So first answer, of course, is the method itself. So STORM it's called, so it's stochastical optical reconstruction microscopy. Works by means of fluorescent excitation. So you have a dye, you illuminate it with some laser light, for example, you excite the fluorophore or the electron, it gets in the excited state, it eventually falls back down in the ground state, and then you have the emission of the fluorescent signal. This leads, according to Abbe, to resolution which is roughly half the wavelength. And if you then pump up the intensity, and also tune the buffer in which the cell is living, you may be lucky that most of the electrons not only go into the excited singlet state, but eventually in the long-lived dark state. So what happens now is like the cell in a way is bleaching, and over time, many of the different fluorophores will start blinking, what you see on the right-hand side. And now the resolution can be defined differently. So you essentially localize every little spot, and then over time, when you localize it, you will end up with a much higher resolution because you know where the photon is coming from. And then if you acquire, let's say, 10,000 frames, you will end up with a high resolution. And usually you have these very expensive cameras I named earlier. So they are in the range of, let's say, well, a small car essentially. And we just replaced the camera very naively with a small cell phone camera. And this was a Huawei by the time, one of the modern devices, which had a special part, and that was a monochrome camera chip. So you were able to capture 4 times more photons, so you don't have RGB filters in front of it. But I think that was merely the only advantage, because all the other physical aspects like the read noise and the essentially everything was much worse compared to the camera we used. However, it was still possible to go from here to there. So 80 nanometers, that was what we were reaching. Of course, still at the problem that you still have the whole device. So you have a computer where you do the reconstruction, you have the whole microscope, eventually the laser module, etc. And what we wanted to do is bring this whole thing to a portable solution. And so we started with CellStorm 2, because CellStorm was the first one on the left-hand side. And here we also made use of a highly integrated photonic solution. So there are some people in Norway, they invented these photonic chips. You can use it for fluorescent excitation, and the way it works is like you have a very high refractive index material, like a silicon wafer, as you may know that from semiconductors. And then you have a structure on this wafer that is like a little slab. So it's 150 nanometers high, and then roughly 25 to 500 micrometer wide. And what you do is you couple a lot of light into these little channels. And then when you have cells sitting on top, they are essentially illuminated or excited from the turf field. So you have a total internal reflection field, or like the evanescent field, which comes from below. And this enables you to excite the fluorophores that sit on top. So you have a very thin layer of excitation, which you then can observe from above. Of course, the problem still is that you need a bulky microscope. That's definitely nothing you want to do. So what we did is we built a small cell phone-based microscope with the cell phone I'm holding in my hand here. Again, monochromatic camera. And so it's just a small optical module that captures the light that is coming from the excited cells here. So you have a laser, you have one of these optical pickup devices, which confines the light and focuses it into this 150 nanometer thick slab. And so you see that it's actually working right here. So you have enough intensity in order to not only excite the fluorophores, but even to do super resolution with cells, with the storm. But let's go one step back. So the easiest thing to do was actually to just wiggle the lens around. So what you see here is a typical E. coli, which we labeled with some membrane dye. And so once you start shivering the lens at the entrance facet of the chip, you see that the discrete mode pattern, which is exciting or existing in the waveguide here, it will move back and forth. And so this becomes a bit like a structured illumination. And so from the variation over time, very similar to the Aurora Borealis, which is actually also happening in the place where these chips are coming from Norway, you can then compute a high resolved image. So you see that here. So this is the full field of view. So you see many, many different bacteria on the surface. This is the sun projection, also the wide field. And then this is the computed super resolved image. So this is using SIR from Ricardo Enriquez group. And you can easily get high resolution also for living samples. And then one thing we also tried is replicating this idea with the help of a neural network, which is cool because you then can just copy that on the cell phone and then do super resolution on the cell phone without copying any data and more or less in real time. So if you're curious, everything is published under the name CellStorm. I can also give you a link later. And then, of course, since well, everybody, I think, was facing the Corona crisis quite recently. And so one advantage of these devices was that we were able to bring one of these devices in our high safety lab where we actually had active coronaviruses. And then we performed a resolution experiment with these viruses. So every blinking spot here represents one fluorophore that's attached to the coronavirus. And then this is the ordinary bright field response, and this is the D-storm response. So you can really clearly determine the virus by its shape. So it's in the range of 150 nanometers. So you would expect some ball essentially as a projection. And then, of course, this is one way to do microscopy, but sometimes you want to do microscopy really, really cheap. And so I think 2-3 days ago, I thought, okay, now is the time to ask the community where can I get this here? Because I know that this is already available. So this here is a small microcontroller. It's called an ESP32 with a camera. So this costs like €5. And I wanted to build a microscope that needs these two ingredients. And I need to know, okay, can I build that everywhere? So that's always something that drives me, so that when I'm having something in my lab here or in our lab, that people somewhere else can also replicate that. And that's often not very easy because people not always have access to Thor Labs or Amazon or whatever. And so I wanted to have something that's watertight, and I knew that these are super watertight because that's their purpose. And by surprise, these glasses from Bon Maman, that's a French jam, are surprisingly widely available. And so if you have these two ingredients, you can also build fancy microscopes, and they look like that. So you have this little ESP32 microcontroller, and then you can simply use these lenses as a microscope objective lens, like a finite corrected one, print a small housing, use the torch as a transmission light, and then you have a roughly 10 euro microscope where you, for example, can do histology samples. Or you can put that into water to, for example, also do all kinds of crazy things in the water. So that's something we're working on together with Manu Prakash. So this is just the first attempt to show you that frugal science actually is also something that can be enrolled on a very large scale. I think that's also a major driving force for all these low-cost tools, so that like once it's becoming very cheap, many people can apply that, and then it becomes a very powerful tool, even though it's not like €1 million and you cannot resolve 10 nanometer. And yeah, these are two frugal approaches to do cool microscopy, I think. And one thing that we're working on quite long now is a system called You.See.Too. And I always like to introduce it that way. So in 2006, I was an electrician, or like I did my apprenticeship here in Germany. It's called, so 3 years of learning how to do electronics. And one task always was like going from an electronic circuit board to, or like the circuit itself, like for example, this is a blinking circuit, to fully functional PCB, and then maybe even further for programming. This always took me ages to build, and usually it never really worked. And so then once I was done, there was this little guy here. So the Arduino is also a microcontroller. It's fully open source. It's community-based, and there's an insane number of parts or like projects you can just replicate, download from the internet to do all kinds of cool electronics without even knowing how to really program these devices. And when I started my PhD here in Rainer Heinzmann's lab, I thought, okay, we have these optical setups. They are always the same, but how come there's nothing as simple as an Arduino, so that we can just reuse the components we have and then also get creative so that people can use it? And so then I observed, or like I think many people observed that already, that the different components, like the light source, the lens, the object, the objective, another lens, and the camera, they are sitting next to each other with a certain kind of relationship. So you have one Fourier plane, or like always focal plane distances, and they come one another. So, and this physical principle, it's already named here, is the Fourier optical principle, so that the Fourier planes follow one another. And that's cool because it's inherently modular. So what we essentially just did is like we took a very, very old principle, drew some cubes around it, and then we called it You.See.Too. And then we started printing around these cubes. So in the very first place, when we had this idea of building a small incubator contact microscope, it was not a cube at all. So we just had a small micro, like a small Raspberry Pi camera with some focusing mechanisms in order to observe cells, like living cells in an incubator. And then we add some more components to eventually have high resolution. And then at one point we decided, okay, there are more people gaining attraction, so maybe why not making components reusable? And then we thought about modules. And then over time we had these magnets, and then some years later we now have injection molded cubes that can easily be put together as simply as Lego, but a bit more purpose specific, not necessarily more robust, because Lego is really, really robust and stiff, and also well engineered for sure. And so what we have now is an ecosystem of many, many open source modules. So if you go to our GitHub page, I'll show you in a second, you will find all kinds of different modules that you can just use for your research, for playing around, or just getting familiar with optics and microscopy in principle. And people have done that. So for example, there's one where so that was one of our very early experiments where we wanted to observe differentiating macrophages. So they become monocytes, they become macrophages, and they are responsible for your immune system. And we wanted to see how do they behave over time at different concentrations of drugs. And then we put many of these microscopes in the incubator and then let it run. And then this is the optical circuit board in a way, and you can easily add more components. So for example, if you want to have fluorescence, you simply add more lasers in order to excite your fluorophores. Here, for example, it's an infection model of some bacteria that are going in some epithelial cells. And this also works over time. And you may see there's some frame coming here. So there's some drift because everything is a thermoplast. And of course, this causes issues over time. Nevertheless, it's surprisingly stable yet, or still. So we're still working on the storm. Actually, that's also where I'm coming from right now. So I just came from the lab to make this work again. So we also have the ability to do super resolution by means of single molecular localization. That's what you see here. And for this, we also use an open source control software. It's called now ImSwitch. And I can have like this, and also structured illumination for super resolution microscopy, where we have a dedicated module that is just that can just be snapped in, snapped out, in order to increase the resolution with this so-called Moiré pattern. There's also a dedicated publication on that, where you can use this module where you already have the laser, the digital mirror device, and the Fourier planes. And so there's no additional alignment necessary in the end. One more thing where it's really becoming helpful is when you want to do 3D imaging. So when I joined Manu Prakash's lab about around 3 months ago, so we had this idea of doing something cool together, because Manu Prakash, he's also doing lots of cool things with microscopy. He introduced me into the whole field of oceanography and plankton imaging, and essentially like a field I had never heard before. And so the core idea was to visualize plankton in 3D. So what you see here is fully computationally modeled, but what we wanted to do is really imaging them when they come out of the water. And so light sheet essentially is working by means of, you have a laser, you illuminate your sample from the side, and then the detection is 90 degrees perpendicular to the excitation. And then usually you use fluorescence as a contrast. And so this is the typical open SPIM. I think there are tons of different acronyms. There's another one which we tried, is the fluided SPIM. So here you have a fluidic system where you pump your samples through the focus and you excite it. There's yet another one, we call it open end. So you just blow your samples in front of the, or into the focus of your lens. And the one I was working actively on in the lab from Manu Prakash is the holy sheet. So that's something very exciting. I'm showing you in a second. So this is partially documented on GitHub, but that needs more care, of course. Just to give you an intuition how easy or complicated it is to build a light sheet system. So we have these sheets where people can replicate, for example, this light sheet system. And every block here represents one of these cubes. So for example, if you have laser, I'm having here one torch in my hand, this is becoming one cube, and then you just place that on the individual position on the grid. And then we give some additional alignment information, and in the end, you will eventually have the fully working microscope. These are the results for the fluided SPIM. And this is the open end. So you just have a small peristaltic pump, fully 3D printed and fitting in our system. And Marie Wilder, who is a researcher in Roscoff, she was so nice to give me some samples, in this case, some algae. And so you see nicely the autofluorescence. So it's way too bright, so that's why you don't see so much. But this is then the 3D response from your imaging setup. And this is now the holy sheet. And so obviously it comes from the mixture of holography and light sheet. And so the idea was, okay, how can we image 3D plankton samples from all different sites, first by means of autofluorescence, but maybe also label-free. And so holography is measuring the scattering potential from your sample, and light sheet has the opportunity to measure the autofluorescence, for example. And so that was one task. The other one was like, how can you do that continuously so that you always have 3D information over time? And so what we decided to do is essentially having a rotating capillary where you continuously let samples flow through. So that's how it looks like right here. So you have, in this case, it's a bead that's fluorescently labeled, and they are going through the light sheet or like through the focus of your lens from one side. So you have one excitation from this side, from the lower end, and one illumination for the scattering from the transmission side. And then you have two different cameras that are capturing the transmission for the holographic part and the excitation from the light sheet part. And so what you see here is in the light sheet. So this is tons of beads that I just labeled in a very bad way, but that's how it looks like. And I think much cooler it looks like when you take actual samples from the sea. So here you have some plankton you usually captured during these plankton tows I've never done before, which was super fun. And so you have a continuous flow and continuous rotation. And it was surprisingly difficult to find a frugal approach to have both and sealed, and also with a flow that is continuous. And so we are about to document all that so that this is also becoming a powerful tool for not only us, because I think it's really nice. And for the reconstruction, I think for the light sheet is relatively straightforward. So here you see again an algae, the Garnardia, and so the light sheet here, what you see here, nicely renders the 3D information of the different chloroplasts, but the reconstruction from the holography is still not quite there. So the computation there is just much more complicated. So, and just for you to understand holography, so holography gives you the opportunity to refocus afterwards. So this is the same snippet I just showed you earlier, and you can refocus the different compartments in the post-processing. So it's like you steer the knob of your microscope while focusing, but you do that after you acquired that. And so, as I said, so it's partially documented. So the Garnardia is also available on GitHub as a standalone device, and soon also as a UC2 component. So that's also nice. You can prototype in UC2, and then eventually, once you're done, you can just derive the optical dimensions to form a small module as this one. And yeah, this is all documented, as you might find that. Another thing where UC2 became really powerful is automated lab preparation, sample preparation. And so that was a work together with Richard Bowman and Wei Yuan, and many others, essentially, of course. But I think those did the magic to glue everything together, where we had the software from ImJoy and OpenFlexure, we had UC2 modules, and also an OpenTrons pipetting robot. And we tried to have a feedback loop where you have an automated experiment, you do the imaging, you eventually also do the analysis on the fly, and then have a decision-making process where stuff will be influenced based on the decision you made before. And so that's how it looked like. We had a small 96-well plate scanning microscope inside the OpenTrons, and an experiment, for example, where we tried to increase yeast cell growth looked like that. So you have a small protocol where first the yeast cells are seeded and feeded, and then eventually the microscope is just going to the well where the growth rate is the highest. So that was our little goal, what you see here. Surprisingly difficult if you're not a biologist like I am, but I learned a lot how to treat yeast cells and how to make proper beer. Yes, and then one more thing towards open science and open source. I think we learned a lot on our way because we never published, patented anything. So everything we did mostly found its way to the public. And recently we also found ways to even better involve the community. So we started asking people, okay, now we need electronics that dedicatedly work for our microscopes, how can we optimize it? And so then we asked people over Twitter, people were responding, and that's where we are right now. So we have a small REST API-driven electronics that is still in the development phase, but it will eventually be able to control all kinds of motors, lasers, and LED arrays with the help of this open source microscopy control software called ImSwitch, there's an H missing, developed in the Testa lab by Xavier. And also there, everything is open source, of course. So if you have questions towards that, I can also point you to some links that help you guiding through the process. Yeah, and also what's cool about open source, I hope I'm not talking too much about open source, is people can use and reuse what you do. And then, for example, there are some people now using our components from UC2 for a completely different purpose. So they had a educational kit for quantum optics. And what we also sometimes do is like we just fork stuff that's available, for example, this XY stage from some people from Paris. And then we introduce that in our small microscope system. And then there's basically no, or not so much effort into integrating external parts. So we benefit from open source hardware, but also I hope others do that. And just recently, shame on me that I'm advertising this paper. It's open access, but I really want to share the message. So we try to share the CID files in our best possible way. I think there are definitely better ways, like the group from Richard Bowman and Julian, they do a hell of an effort to really make sure that everybody has access to these CAD files and really everything is under version control. We tried to do our best to do so. For example, recently we did a workshop completely online and people were still able to follow everything by means of fully digital documentation with YouTube videos. And so, yeah, for us, the question whether open source is helpful or not, it's definitely yes. And this is also reflected by a huge community that's constantly growing. So we had many different workshops, and I think also many people all over the world are using the blocks and printing it at home and putting their ideas into form. Yeah, and I think with this, I would like to end the talk and definitely thank the two groups I was part of, or I'm lucky to be part of in Stanford and here in Jena. And yeah, I'm really lucky to be working on this project because we don't really have any official funding. We're just lucky that sometimes people just like it. And yeah, so of course I'm not alone. There are many people also actively working in the UC2 project. Haran Wang, Barbara Marsikova, Sven Karlstedt also doing the biology part, Rini Lachman and Edda Minkel. And yeah, so I hope you have tons of questions. If not, I can definitely also give you a quick tour through our GitHub repository so that you have a better idea where you can start.
Thank you very much, Benedict. That's very interesting. And please talk a lot about open source. I mean, this is a topic we're interested here, so no problem in you discussing all that. So if anyone has a question, please raise your hand and we'll try to organize that. Perhaps I can start with one. So Benedict, I think in many of these applications of open source tools to microscopy that I've seen, there are some performance evaluations, for example, how much resolution or precision can you get from these systems? Where do you think are the limits? Like, are there fundamental experiments that you can, I mean, experiments that you can do in these kinds of setups and others that it's impossible? Can you comment on that?
Yeah, that's indeed a very good question. So usually people come to us and say, okay, we have this application, say this infection model of cells with bacteria, and then they want to have two different laser wavelengths for excitation, and they want to do that in the incubator. And I think I'm always a bit too naive that this will somehow work out in the end. But of course, you will always face problems on the way. So for example, sometimes components will just break, or the stability, since everything is a thermoplast, it will just bend over time, but you learn many different lessons. So for example, for the plastic, better use some PETG instead of PLA, because PLA is just, it's just melting away. And then also you find different publications where people use different cameras that are maybe more sensitive, but still low cost. And I think also one thing we definitely learned is if there's a possibility to buy it for a reasonable price. For example, I have the best example laying here on my table. So this is a small, if you can see that, this is a small stepper motor that's linear. And so I put lots of effort into designing something that's completely 3D printed and open source. Well, you don't need to have external parts. So this here is, I think I just turn off the shading thingy. So this is a small motor that costs like, I don't know, say 50 euros. And I wanted to try really pushing the price down, but sometimes it's just not worth the effort. So you spend way more time, and the results by far not as good as something you would just buy off the shelf. So I think in the end, you can achieve quite a lot. So maybe not like 10 nanometer precision in terms of motion, but if you know how to compensate the cheap with low-cost alternatives, I think you can really achieve a lot. If this helps.
Yes, very helpful. Thanks. Super interesting. So I think Tobias has raised their hand. So please, Tobias, go ahead.
Hi, Benedict. Thanks a lot for a very interesting talk. Sorry for joining sort of a bit incognito today from my so I would like to ask you a little bit about alignment. So I understand that an important use case that you use the UC2 for at the moment and in the workshops is to understand light paths and sort of prototype them very fast, but you wouldn't necessarily, as far as I understand, just use this as a final setup to run, let's say, for a year for research experiments in the lab. And I'm wondering if I think I understand that one of those reasons might be because the alignment is a little bit more fragile, so you might have to realign quite a lot over time, for example. But I'm wondering if there's any, first of all, whether this assumption is true, and then if there's any ideas you have maybe to compensate it. For example, inserting some cage rods or something like that that give it extra stability or something like this.
Yeah, that's a very good point. Yeah, I think I was just thinking about setups that survived a long time. So essentially, yeah, we don't have setups that run for 2 years. So I think I see our system more as an enabling technique. So for example, if this person who wanted to observe this infection process in an S2 or maybe BSL3 lab, there's just no access to these microscopes at all. So this is the first study of whether it makes sense to maybe dig deeper. That's one thing. And for sure, it definitely challenges your alignment skills a bit more than you do that with Thor labs. But so I don't have one here, but usually, I mean, the alignment modules, so for example, the kinematic mirror mount is pretty similar to the one from Thor labs. If everything stays in the same temperature range, there's not so much alignment necessary. But of course, if the temperature is varying, like say you do that outside or so, then 10 degrees means like the whole system is misaligned. And I think the best example where we had to do quite a lot of realignment in the process was the structural illumination, since you use interference to form the final structure. And we also quantified that by using a microscope interferometer. So you can just use a laser, split the beam, and then see over time. So we did that over 2 nights in the lab, how the stripes are moving. Maybe also because of the laser, the quality wasn't so nice that there was lots of phase jumps, but you see that there is some variation. So of course, it's not as stable as like a Zeiss microscope, let's say. So if this helps answering your questions. And for visualizing the process, for example, right now we work on the open spin, which will be bringing light sheet, for example, to places where this cannot be used because it's too expensive, like Nigeria. And I think there it definitely makes sense that you have everything under control, but still access to the technique itself. So you don't need to rely on Thorlabs components that are worth maybe, I don't know, say 100,000 euros just to see maybe a zebrafish GFP expression or something like that. So I think we're not directly competing with Thorlabs, but we're not too far away.
Thanks. That sounds really interesting. If there's no other urgent questions at the moment, I would follow up also the related idea. So one of the things that I always say that's relatively or comparably easy to do with open hardware is to automate things. So it's quite easy to put an extra sort of motor or flex stage somewhere in your path. And I guess that can also be a possible alternative, right? Have you thought or explored this idea of having self-aligning setups, for example?
Yes, yeah. So luckily or interestingly, I don't know. So there's the Lichtwerkstatt. So that's the German phrase for optical workshop. So it's a hackerspace only for optics. I think in Jena, that makes sense. So it's next door. And so they develop these kind of things. So they have a micro-interferometer with our components where they add some motors to the knobs of the kinematic mirror mount. And then you can remote control that. And that was born with the idea that people during COVID did not have access to the lab and they should have done that from home. And the next step is actually even further going only on the screen, so that, or like you have your cubes and your screen, and then you do some augmented or virtual reality so that you have both components there, so that you can align virtually, and then you maybe see what's happening on the screen, and then you can copy that into the physical world. Yeah, so you can easily add motors. So there's like tons of motors from CCTV, from Chinese surveillance cameras, where you have small XY translation stages. You could just mount a lens to that and then use it for auto alignment, for example.
Awesome.
Very good. Thanks, Tobias and Benedict. Very interesting questions. So I actually have another one, but for anyone in the audience, please raise your hand, and we have time for questions. So let's not be shy. But the other one I had in the meantime is that I wanted to ask about what's your perspective? What do you think are the possibilities for commercial opportunities around this? So, for example, it could be interesting if I could buy a UC2 microscope as a cheaper alternative to other more established, perhaps higher, more supported versions. Or another example is, for example, I could. It would be perhaps interesting if I could buy the 3D printed, sorry, the injection molded parts, right? So I can build my modular setups, right? But the injection molding, which could be perhaps more stable parts, those would be super challenging for individuals to do by themselves, right?
Yeah, that's a perfect question. And so, yeah, many people are asking for all kinds of things like cubes and individual setups, mostly also for university courses. So we always have the problem that we're inside this institute and we cannot really do anything beside a research project. So our project is in a way very special because it's a product in a way because we went quite far, but still we do research because we support researchers with instrumentation that enable research. And so now to have like a legal way of performing exactly what you were asking for, like giving or like enabling people to get these tools, we are thinking about ways to scaling up the production. And there are some interesting parts. I think also if you Google it, there's a company called LabMaker. They also produce the Open Flexure, for example, and their model is producing open source hardware. And so we, with the help from those entities, will hopefully be able to come by what you just said. So having for example, the boxes for schools ready, and then finding some kind of business model that this is self-sustainable, because open source hardware is really difficult to do. So there's like only very few companies that do that well. For example, OpenTrons, I think it's just too expensive, like too complicated to replicate it. But if you ask people for help, usually the first question is like IP, and open source is not there yet. So I think maybe in 10 years or so, more people like even Zeiss and Nikon and stuff, they may think about going this way. But right now, I think open source is not yet a business model. So yeah, kind of hard, but we'll go there. So expect something more during the summer.
Good, thanks.
Sure.
So I think Andrea has a question.
Can you hear me?
Yes.
Okay, awesome. Thanks a lot, Vicente, also for the encouragement of asking questions. So Benedict, so first of all, congratulations. Looks like you guys are having a lot of fun. I kind of envy you for that. My question is related somewhat to what Vicente was asking on the commercialization, because making something commercial available also makes it available for people that don't have engineering expertise. So it would allow also biologists, medical doctors to have this type of instruments. So are you moving in that direction? So also making somewhat the things available for production, or on the other hand, are you taking actions to make this type of approaches also more accessible for people without an engineering background? And then the second question I have, you got my attention with the OpenTrons, and I was thinking, I mean, you got my attention also before, but curiosity there is because you have systems that are relatively cheap. So why not to mount, I don't know, a 96 well array of these optical pieces, so that at the same time you can just take an entire iris snapshot of a 96 sample, just as an example, can be a 6, something like that.
Yeah, so I think I identified two major questions. So taking the second one first, the 96 well plate imager. So we're not quite there with the 96 well plates, but 24. So we have a prototype that's not, well, it's not really working yet, because the ESP cameras are quite cumbersome sometimes. But yeah, this is like a perfect use case for low-cost hardware for sure. So once it's done, it will be shared for sure. The other thing with the engineering, so maybe I'm just sharing my screen once more, showing you our GitHub webpage. So maybe for you or for others, so this is our major GitHub webpage, and so what I was talking about with the boxes is something not only for engineers, but for elementary, high school, and university, and maybe also engineers. So we have different boxes. For example, the mini box is something we'll be producing very soon for schools here. So this is only ray optics, where you learn what's a telescope, what is a microscope, but you can easily scale it up. So for example, if you want to have some more polarization in microscopy, or like not microscopy, but the polarization experiments, we also have that. And also something that's the full box. So then you have light sheet, and you have Michelson interferometers, and everything comes with the documentation. So we guide you through the process of, okay, so this is what you want to achieve in the end, and then go step by step, little by little. And I must admit that this documentation is already a little old. 2 weeks ago, we had this workshop. So for this, we had this workshop repository. So if you go through, there's even a process really like step by step, in the hope that people can also do that without us, so that you get general introduction. That's what it just showed. But also start with a feasible experiment like an inline holographic microscope, give you a bit of an intuition how to build it and how to set up the software. And yeah, so I think the next step would be, because I think people don't necessarily have access to all the components, and it would just be nice to have a whole set which you can just purchase, that we go this step for them, and then they can get that from some source. Let's see. And yeah, but that's coming soon, I hope.
But thank you.
Sure.
Thank you, Benedict and Andrea. So again, if anyone has any questions, we have a few minutes, and so it's no problem in using efficiently the time of our speaker. Pierre, please go ahead.
Okay, well, first of all, thank you, Benedict. More than a question, I have a comment, and I just wanted to say thank you for sharing this project. Actually, we have replicated the U-blocks here in Santiago. So we are using this for a project. Just to share with the participant, we already modified one piece for a lead matrix. So
nice.
Yeah, we will test these pieces, and then, well, we can share what we get.
Nice. That's awesome. Yeah, it's always a pleasure to see people really using it. So that's awesome. Thank you so much. I'm excited to hear more from you.
Thanks. Any other questions?
Maybe I can just add another comment as well. So we obviously invited Benedict here today for this presentation, also because we're a huge fan of this system. It's a very cool environment that you've created there with all those modules. And so we are also planning to host some Latin American workshops with these components here in Chile. And we'll invite researchers from across Latin America to come join and learn how to use the system, and in at least one workshop, hopefully also be able to take final assemblies home with them. We don't have any final dates yet, but I just wanted to bring that up again, that this opportunity will come, and we are already talking when we can have access maybe to some sets so that we don't have to print hundreds of parts ourselves.
Yeah. Even though I must admit, so as much as I'm a fan of 3D printers, there's nothing that's coming close to the precision of the injection molding. So I need to say that even though I really like the 3D printing, and it's still possible with 3D printing, but if you want to build, for example, the structural illumination microscope, it's just so much easier and less painful if you do that with the injection molded parts. But we're working on that, so expect something to be there soon. So really soon.
Yeah. Well, I also just visited the Prakash lab here in Stanford, and was quite impressed that they use very little 3D printing actually, and a lot of machine parts. So I guess that's also an alternative route. I haven't really tried this out yet from Chile, how easy it is to get things shipped, custom machine parts. But I guess that's another way of getting different precision levels potentially.
Yeah. Also, laser cutting is actually surprisingly stable and it's fast, way faster. So we also have laser cut versions if you go through the step. So this producing one of these parts is like less than a minute, and for the 3D printed parts is like, let's say, an hour or maybe more, depending of course on what you want to do.
Excellent. Thank you, Tobias. Thank you, Benedict. Yes, so with this, we end up our first seminar in our series. And so we're really glad to have had Benedict share with us his talk. And I will just invite everyone to pay attention to future announcements for the next seminars. We will be sharing these, and also probably a calendar, the workshop that Tobias was mentioning as well. We plan to make available these talks online, and so you will be receiving more information in the near future. Thank you very much, everyone.
Thank you also very much for inviting me. It was really nice.
Oh, thank you.
Bye. Thank you.
Thanks. Bye.
Bye.
Thank you.
Thanks. Bye-bye.